Okay, everybody, welcome back from the coffee break. I think the last part here today is the opportunity to give expanded questions to the two teams from Hydroterra and from Keystone. And basically, it's open for broad question or specific question. And we'll see when there's no more questions and the sunshine outside, we'll just break for today. So, open. Somebody has something they really would like to know? Yeah, on the back.
So I would like to take the opportunity to ask a question to the Keystone team, which I was not able to do so earlier to the time. So so Keystone does measure atomic oxygen, which we have heard is a very abundant species of the upper atmosphere, but atomic oxygen itself is also very reactive and does play a role also when it comes to satellite or instrument surfaces. I would say it's also important just to know about the variability of atomic oxygen due to this engineering question, but I wanted to ask how you see this topic. And why?
Is it on now? Yes, okay. Yes, Patrick Espy from Norwegian University of Science and Technology. Yes, my background was building far ultraviolet spectrometers for space, and we initially thought osmium would be a great coating because it's so highly reflective in the extreme ultraviolet. But it also forms osmium 04 and evaporates at shuttle altitudes in about a day and a half. So, you know, from that background, any optical coatings are particularly vulnerable, but also spacecraft structures of carbon fibers, things like this are very reactive. So knowing the atomic oxygen flux in which you're going to have your satellite flying through, then you can also engineer how much protection you need, how much sacrificial material you'll need for your mission lifetime. So it has an impact on satellite design. So knowing the atomic oxygen density very well globally and how it varies will impact satellite design and cost factors as well.
I did some research on this topic a while ago, and what I came across were papers, and they used empirical models like NRL-MSIS for the density. From that they estimated atomic oxygen and then did the studies that Patrick just described. So to the degree that we can better predict density and in particular atomic oxygen, that would directly improve such models and therefore satellite design.
Yes, just to add on, since a lot of the optics we designed for were for space shuttle instrumentation, so it's really it's an important problem both at spacecraft altitudes or at shuttle altitudes all the way up, where atomic oxygen is the major density or major species.
Okay. We had one, yeah, that was Carla.
Just as a follow-up, I think that will be particularly important when it comes to VLEO, which is now targeted more and more, also from space.
Yes, I can emphasize that. So VLEO will be increasingly important because there are spacecrafts under development for VLEO operation, for more or less permanent VLEO operation. We will probably see the use of VLEO as a more or less regular orbit in a 10 years period from now. And for that one, it's extremely important to understand the atmosphere at altitudes around 200 kilometers. So we are with Keystone, we are exactly timely for the use of VLEO for spacecraft.
Then it was Carla?
Yes, I had a question to Hydroterra. So thanks, it was a very nice presentation, very interesting. I was interested in your products on these snow water equivalent and the melt events, and I was wondering if you think these could be useful on a European-wide basis for water reservoir management on one hand side, maybe also for subsurface water management. And if you think that this satellite is flexible, sufficiently flexible, that it could be used to go and observe one area where, due to any pre-monitoring effect, you think maybe a disaster could happen, so you could switch on this area, whatever your ROI in that year is, so to make a better disaster prediction and then also disaster monitoring. And I was thinking both on floods, but it could be also for, you mentioned the volcano observation, which was very detailed, so also more detail, which from the 1 kilometer resolution, which in the text you say it goes down to 100 meter resolution, and I think that could be a very useful product.
So first for the snow, I think we are observing two major parameters of the snowpack. So one is the snow mass, and which determines in a basin how much snow is accumulated within a certain time period. And when we concatenate the different observations on a daily basis, I get the overall amount of snow water equivalent in this basin or in the area of interest what we are observing. This is a parameter which is not known so far. So you know that remote sensing community was looking since 20, 30 years for getting high resolution snow water equivalent in mountain regions. And this is still the holy grail of snow hydrology and for monitoring snow. So this is not possible so far. But Hydroterra is not looking alone to this. Also Roselle and L-band missions will look to this parameter, but not on a daily basis. They will look on a 6-day basis on this. And these missions will be available on a global basis, providing this also for other mountain regions. Next to the amount of snow, it is also important when the snow is melting. And for this, we are using the C-band data, the same data set, what is required by Hydroterra Plus, in order to determine when the snow starts melting and when the water is released from the snowpack. So it's not immediately when we have the first snow melt on the surface that the water is already coming out from the snowpack. It takes some time. And for this, it is important to monitor also the refreezing of the surface of the wet snowpack. This happens in general during the night periods, and it is also important if the cloud is free of clouds, if the sky is free of clouds or cloud covered, because this determines the energy budget on the snow surface. So long wave radiation was mentioned during the presentation, and we calculated the different fluxes for this, and this is a major this energy fluxes is a major input for the timing of the runoff, if the surface is refrozen or not. In general, just to give you an idea, over a clear night in the Alps, the crust formation is about 10 centimeters of thickness. But it has an impact on the long wave radiation and on the timing of the runoff. Both together, the amount of snow in the basin and the timing of the runoff gives us a better view to when the snow melt is contributing to this. Another point is precipitation, and this is coming now to this disaster one. When precipitation, so liquid precipitation, rain is falling on the snow, then of course these situations where snow melt plus liquid water can form big floods. So these situations when we have warm temperatures up to very high elevations, then we have precipitations, and this is forming these floods. And also, again, the amount of snow, what is still there in the mountains at the time that this happens, is important for this situation. Okay, then for the disaster, maybe Harald has...
Maybe again what you mentioned in the introduction, to emphasize again how important it is to understand snow for explaining the declining groundwater levels. Because usually, when is groundwater recharge most efficient? It is efficient when, let's say, around March, when the vegetation is not yet fully active, and when the snow slowly smelts, and then that is actually the time when groundwater recharge is highly efficient. Now, with all the global warming and the regional amplified warming, we have less snow, so there is less snow water available in March that can infiltrate and then provide groundwater recharge. So, to understand and maybe to cope with the declining groundwater recharge, I think it's of utmost importance. We need to understand the snow. And, of course, we are not covering full Europe, but with the greater Alpine region, with the Pyrenees, with many mountain areas, also in the Greek region, we cover many, many regions where snow still plays a major role.
And maybe when we come now to the application of this product, you're right. This information is highly needed for managing hydropower reservoirs, for managing water resources in the Alps in general. Because also when we look for irrigation, there is a need to know when the water from the snowmelt is coming and how much is coming. So both information, so how much resources we still have in the mountains in order to can irrigate in the plains and so on, far away from the mountains. So this information is essential. And the timing and the amount of water is a critical information for this.
Okay.
Yeah, just to respond to the flexibility part of the mission in particular, there's two aspects to that. One is there are these 4 taskable slots that we envisage that are completely free every day, so we can point those wherever we want within the visibility region. And so I anticipate, for example, weather forecasts are predicting a high likelihood of an extreme weather event in Spain, but we're focusing on the Alps for that particular season. We move those taskable slots over and stare. We can also then go in a more extreme mode and say, actually, we really want those hourly observations, those 20 observations per day. We can actually just switch very flexibly the mission to completely stare at a region. So maybe this is, Vesuvius goes into a phase of unrest. And then secondly, you mentioned about the resolution, and for that deformation mode, I guess the equivalent single look resolution is 30-40 meters by 30-40 meters, something like that. Sentinel's higher resolution, so that's 20 by 5, but it's not outrageously different, and we'll do some, obviously you do some averaging. The other advantage you've got with Hydroterra Plus is, particularly if you're in the staring mode, you can integrate over a longer period of time and get a higher resolution, or you can basically trade off that temporal and spatial resolution. So you could go lower spatial resolution and higher temporal sampling. So we've got that complete flexibility, which is, I think, unique because of this imaging geometry. Yeah.
Okay, we have another question in the back.
Thank you. Peter Schad from DLR. I have a question to Hydroterra. And my question is referring to a previous Explorer candidate that was here in the competition, Core H2O. It was a mission dedicated to the measurement of snow water equivalent. And there the choice of the frequencies were, when I remember correctly, X-band and KU. So, and now you are choosing the C-band to measure it. It's come a little bit as a surprise for me. Is this really the optimum frequency to measure this parameter?
Yes, I was also involved in the Core H2O planning 20 years ago, or 15 years ago. At Core H2O, the retrieval algorithm and the approach was different. We were using X and KU band, and we were using backscatter data, so only the intensity of the backscattered signal, and we retrieved the snow water equivalent by the interaction with the grains of the snowpack. And we had to solve a couple of issues there. For example, the dependence on grain size, on the layering, because this volume interaction between microwave at 2 frequencies and the grains depends, of course, also on the grain size. In Core H2O, in Hydroterra Plus, we are actually using a different approach, which is based on SAR interferometry. And what we are measuring is here the phase delay at C-band in the newly accumulated snow in the time interval when we are observing this. Why is it not done with Sentinel-1? That's one question, because Sentinel-1 is over 6 days, and the time period is too long in order to keep the signal coherence. Over a time period of 1 day and also or 12 hours, which is the goal, we can keep the coherence, as it's confirmed by airborne campaigns, by the Sidankela measurements and other observations. And with this coherence, we can measure very accurately the accumulated amount of snow mass, so snow water equivalent, independent on the grain size and almost independent on the snow density. And the effect of snow density is very small because it's always fresh snow and we have a quite good adherence on the fresh snow. The same method with SAR interferometry will be also applied to L-band, like it's tested with NISAR, but also with Roselle later on. And L-band is much less sensitive to this temporal decorrelation. Therefore, it's a longer wavelength. And therefore, we expect that over 6 days, we keep the coherence. And that is also confirmed by already ground measurements and airborne campaigns. So we prepare for this. And Hydroterra will fly in the same era as Roselle. And of course, a combination of both SOLEO and GEO orbits will give a more detailed figure on that.
Oh, yeah, down here, and then Vincent afterwards.
Yes, I'm Stefan Buchert from the Swedish Institute of Space Physics, so I'm coming from above. A question to the Keystone. There's, of course, also the ionosphere in that height range where you do the measurements. And you're obviously not directly measuring the ionized part, but the atomic oxygen is very important for determining what happens there. If you ionize, the O becomes O plus and it stays forever, while if you ionize an NO, it will very soon disappear and recombine. So have you thought about checking what you can do for the ionosphere community, for the radio wave propagation and all these things that have to do with the ionosphere? Or are you planning to address that maybe in phase A?
Is it okay? Okay. So thank you for your question. Luca Spogli, Italian National Institute of Geophysics and Volcanology. Of course, Keystone holds a lot of potentialities for ionosphere. It was actually listed among the interested communities because MTS holds the keys of the electrodynamics of the ionosphere, because all the electrodynamic, all the spheric circuits is there. So every variation in the winds and every variation in the neutral plasma collision change the electrodynamics. So you can use Keystone to proxy the changes in the electrodynamics. Additionally, the E and D layer of the ionosphere are within the MTS, and E layer irregularities are very important for GNSS satellite navigation and for HF communication. So for instance, in the polar cap absorption events that occur and change the chemistry of the D layer are very important for space weather application, especially for the aviation community. And for instance, also sporadic E layer is a typical E layer irregularity which is driven by the interplay of the metallic species and winds. So somehow Keystone will contribute a lot to the ionospheric physics, especially for irregularities and electrodynamics, and of course auroral irregularities, because they are E layer irregularities mostly, and they give a lot of troubles on on technological systems.
Yeah, John Plain from University of Leeds. We are going to measure O+ directly, so that will be part of the mission, and the other ion we'll measure is Mg+. As Lucas said, that's very interesting for looking at sporadic E. So we will have some information about winds, about the metal ions, and Mg+ is obviously a marker for Fe+ and Si+ and the other meteoric metal species. And the chemical lifetime of sporadic E is controlled by O and ozone between them. Ozone oxidizes the metal atomic ion to an oxide ion, and then that can undergo dissociative recombination. So we can actually do a fair amount on the ionosphere, and it's only obviously part of the overall mission.
Okay, det was Henri Vincent.
Thank you. I have a question for Hydroterra Plus, Vincent Ripper, HEO and ECMWF. So I'm fully sold to the science questions that Hydroterra Plus is addressing, revealing hourly water dynamics. That's clearly important. Where I would like to ask you the question is to convince me maybe more on why a satellite is the best way to complement the observing system that we have today, as opposed to field campaigns or reinforcement of ground-based observations. So I think it's important maybe to, I'm playing a little bit the devil's advocate, but to formulate why a satellite on geo-orbit is the best or the most cost-effective way to unlock the elements that you've identified in the report and in the presentation.
Well, let me start maybe general. We see worldwide, Africa, but also in Europe, a decline of observation stations because it's expensive, it's difficult to access. It's difficult to access in mountain regions in particular. And we need this spatial figure. We need this spatial figure, and that, of course, can be very efficiently done by satellites. But we always still need additionally the ground stations because we still need to do ground truthing, we need to calibrate, you know. But we can only afford in specific points, in specific observatories, we can afford very specific comprehensive observations, learn and train and estimate how good the satellite product is, and then take this to the spatial regionalization. But that is just in very general, but let us be aware it is expensive and it's difficult for many countries now to afford that.
Just one key point is that with satellite data, actually here we are looking at high spatial and temporal resolution. The gradients we can see from spatial data of satellite data. We cannot get from any kind of field campaign. Field campaign can be very dense in space, but can be 1 week, 2 weeks. We can put several stations, but we will never see the gradients. The gradients is quite crucial if you want to investigate the water cycle at this resolution.
I can say that there is a complementary between Hydroterra Pass and the scenario of other Earth observation sensor. So we have passive sensor for all frequencies from microwave to the infrared, and then we do have active sensors that are different because they observe all day, but they have also a reasonable resolution. And in the active sensor, we have active sensor for P-band and L-band and so on, but no of this active sensor with high resolution, that is like a synthetic aperture radar, has really the temporal refresh to observe something in the range of the daily change. So I think that we have, of course, GPS has a capability to observe with a very fast temporal refresh, but GPS is a point-wise. Either you consider it or radio occultation. This is very sparse in the space domain. So I can see this as a complementarity observation system respected to the other that already exist.
Hi, this is Steve Hobbs from Cranfield University. Just a couple of other points. We have actually looked at alternative ways of doing the Hydroterra science. So not within the ESA studies here, phase area, but team members. So for example, DLR have looked at a low Earth orbit constellation of small satellites. They turn out to be more expensive. We've got relatively small footprints. And we've been doing some work at Cranfield looking at, say, using HALE platforms flying at about 20 kilometers with a radar. And again, they have such small footprints, you would need a huge fleet of them, and the expense of that just means it doesn't compare well with a geo-radar for the science that we want to do.
Maybe one quick reply to this also. We are moving really from a photograph to a kind of movie. We are really observing on an hourly basis the processes, what is going on. Currently, we do this with a few days. And this, I would say, this is a really wow effect, what was mentioning one of the questions, I think, by Klaus before. The wow effect is that from space, we can really track on an hourly basis what is going on Earth. Okay, only for a certain region, but this for Earth Explorer is a big step forward, the same as we had from Envisat with 35 days to 6 days, and now we are going from 6 days down to an hourly basis. So this is a big step forward in looking to a totally different kind of processes, which we cannot observe with any other mission in this temporal high resolution. And the learning effect will be immense, in my opinion.
Yeah, just go ahead there. Okay. Any more questions from the audience? Maybe I have one for Thomas, especially Thomas Nagler. We all know that snow changes a lot and the snow melt comes immediately and stuff like that. But if there's a question about C-band and snow water equivalent, could you imagine, now we think 10 years ahead, could you imagine other missions basically calibrating kind of the accuracy of SWE? I'm thinking about the Ka-band mission, like SWAT, plus the new optical LiDAR mission, EDGE. They could actually measure this pretty accurate, I'm pretty sure, but it's not done yet.
Yes, it's not done yet. For SWAT, actually, we are looking into this. And the basic idea is that we are changing. So SWAT is sensitive to height elevation, and what we very accurately with tens of centimeters accuracy. And when we have wet snow, then of course we have no penetration at Ka band, and then we can have a time series of DMs, so maybe without snow, and at the end of the accumulation period with snow, and then by DM differencing, we actually could observe, at least for flat terrain, a kind of snow height changes. So that it's not a direct measurement of SWE, so it's not the mass, but it's a change of the snow. So that's very, very experimental.
But you had EDGE coming up, which is 60.
Yes,
LiDAR
of course. Yes, so, but it's a lot to do for the future.
Well, that's good. I mean, we have a snow mission, which will be very, very accurate and calibrated by other missions, and ESA and NASA cooperation down the line.
The point is that those missions are not designed for mountainous terrains.
Of course.
And there it's hard to apply. And there the solution of a SAR is currently the only way to get snow water equivalent or snow mass changes.
Thank you. Questions? More questions? Comments? Okay, Rune and Torsten, should we say, if there are no more questions, close today?
Are we really going to dismiss the teams? Okay. Yes, Carla, please.
Maybe have one question, because for Hydroterra, again, so in the presentation today, you said the mission could go 7 years long, and in the now description, you would have one region of interest every year. So in 4 years, you have 4 regions of interest. What would you do if the mission goes longer to 7 years? What would you do with the 3 years?
I think that's a great question, and we'd really like to get the community involved. And I could even see us having a formal mechanism, a bit like people do with telescopes. You know, you bid for some time to observe something you're interested in. It would be fantastic to open up this kind of radar observatory so that the community can bid for, you know, 3 months of observing time for their particular area of interest. I think there's a huge amount of science that can be done. We've thought of some ideas as a MAG, but we'd be really keen for other ideas. There's certainly some ideas looking around Germany, maybe Scandinavia. We want to test the limits of what we can do, but I think we'd be really keen to have a kind of open call for the later phases of the mission to try and open up some additional science. I think that's a really exciting possibility for a mission like this.
One to the Keystone. You pointed out that the measurements you are doing are actually also very important to the 20 years of SABRE measurements and other measurements you have done before. So actually, the impact on time is actually much longer than your own mission period. How can that help you really to maybe see a little bit better what's the influence from above and the influence from below us?
Yeah, so the heritage aspect of it, I think, is very important. There are missions back from the 90s, Windy, Hardy, and then there's SABRE. Right now, each mission has its idiosyncrasies, so if we can calibrate and get the chemistry right, we can certainly get an idea of what the time series and the variation of atomic oxygen, possibly also the variation of the mesopause region, this kind of thing. And having that would make it a 30, 40-year heritage that we'd be able to get at. The degree to which you can see what's going up and down probably is a bigger problem, but certainly knowing what's going on with the mesopause and the amount of atomic oxygen would certainly help address that and provide complementarities that could be used for these other missions as well. So I think it's, it's an important aspect of Keystone where, yes, we have the 5 years, but if we can get the chemistry, we essentially have a 40, 50-year heritage that we help solve.
I mean, the changes over that time we know about are increased methane coming up from the stratosphere, which is then converted to water. So that will have started to have an impact. And we know that this part of the atmosphere is cooling rapidly because of greenhouse gases that above 20 kilometers act as radiators rather than trapping heat. And so there are a number of changes one ought to be able to see over 40 years. I think that would be a very exciting thing to do, to have a fully calibrated data set going back at least to the early 90s.
Maybe by standing here, there will be more questions. It doesn't seem so. Okay, so maybe I can just ask you to sit, because then this will be very quick. Can I get the slides from this morning up to see what is going to happen next, just that you are all aware? So we have 10 minutes of margin. First of all, thank you very much to the teams for excellent presentations. Yeah, there's no doubt about that. And to the audience for participating. You have done exactly what we asked you to do when we started the day, namely to ask questions and to probe into the nature of this mission, so that's great. Right now, the time has come for us to relax and celebrate a little bit together. This is just the slides from this morning where we said what was going to happen. So there will be buses leaving from this hotel at 6 o'clock. From the lobby. well, the bus, hopefully not inside the lobby, but from outside the lobby, from outside the hotel. Yes. We have seen posters and teasers for joining the Fotografiska in Tallinn at the airport, so I guess that this will be an exciting place. As was said also this morning, there are buses taking us back if you wish, but if the weather is allowing it, it's also a very nice walk. So that's what's for the program for tonight. So there will be a bit of material for relaxing and for spending good time together. Tomorrow morning, we start with coffee, as far as I know, at, next slide please, at 9 o'clock. And the proceedings here in this room will start at 9:30. Yeah? And then we will go with ECHO and finally then with CryoRad. With that, thank you for a great first day, wonderful day. Thank you again to the team. Let's celebrate a little bit this wonderful work that has been done together and just enjoy the evening. See you in about 1 hour.